to the Polarity and mixing a lesson today. So we are going to continue our study of the properties of water, and we're going to look at why water is a good solvent. Okay, so I don't know, a few lessons ago we talked about how we have a solute, so like maybe um, sodium chloride, right? Solute powder. We're throwing it into water. Water is the solvent. We mix it up and then we make a solution. Okay, so we're studying how water is a good solvent. So you have the greater quantity of it, and then we'll dump stuff into it that can mix. We're going to start with looking at ionic compounds. So we're going to use sodium chloride being dumped into water here as an example. So again, this sodium chloride is the solute and water is the solvent. Okay, so you guys know we've studied ionic compounds now, and we looked at comparing the different types of bonds the other day, and so we knew that sodium chloride is an ionic, okay, has an ionic bond, okay, that holds it together. And so we know that ionic bonds are the strongest of all the bonds. So so like when we were looking at the melting point and the boiling point and so forth, they were really they were much higher than the covalent compounds and so forth, right? So we were, when we were looking at this, we were just looking at sodium chloride on its own. We didn't mix it in anything. We didn't do anything to it. We just we just added energy, so we added heat to it. So if you try to take sodium chloride, the solid, and melt it into a liquid form, you have to get an 800 degrees Celsius temperature added to it. If you are somehow get it to a liquid and then you want to boil it, the temperature here's the temperature here. Okay, so so again, it takes a lot of energy to overcome that ionic bond. It's really strong. Okay, but when you now take this sodium chloride and you dump it into water, there's a different story that happens here now. So I want you to take a look at this diagram here. So this is, here, I could show you this one here. It's like kind of alternating sodium, chlorine, etc. Okay, so say we just take a little crystal of sodium chloride and we throw it into water. Okay, so this is what's happening. So again, the purple here, the little one is sodium ion, and then the bigger circle here is the chlorine ion. So again, when it's a solid, it's really strong. But when you throw it into water, what happens is that water is polar. So we studied that. It's got a slightly negative end and a slightly positive end. So here again, the red, bigger circle here is the oxygen. Okay, and then these white circles here, that's the hydrogen, okay? All right, so again, remember, it's a bent molecule that goes like that. Okay, so what's happening here is the water molecules will come close to that crystal of sodium chloride that you threw in. And because you have these slightly charged ends, they will orient themselves and almost cause interference with the ionic bond and weaken the ionic bond that is between sodium and chlorine here. Okay, and so again, these ionic compounds will, they'll organize themselves nice and neat because they're charged like this, so they can kind of organize themselves in a nice tight bond here like this. Okay, so basically what happens is these water molecules will come along and actually cause interference, and then it'll actually weaken the ionic bond to the point they break, and then you end up with the chlorine floating away, the sodium floating away. Okay. What will happen here is that when the chlorine floats away, the water molecules will surround it, okay? And same with the sodium here, they'll surround it. But if you actually take a look carefully at how they're oriented, the water molecule, again, even when it came near the crystal before it broke apart, it moved itself in a way so that, so if the sodium's positive, the negative end of water hovered close to sodium, okay? Chlorine is the negative ion, so the positive end of water, okay, see how it moved itself around, and so the positive end is closer to the negative chlorine here. Okay, so that, and then it causes it to break apart, and then when it's in just on its own now, same thing, the water will now surround it. But then again, the slightly negative or slightly positive end of water is actually facing the negative ion. And for sodium here, the slightly negative end, which was the oxygen here, will be facing the water, or so the sodium. Okay, so I have a diagram here where all the oxygens and hydrogens and sodium and chlorines are kind of labeled, so you can see what's going on here. But it's the same thing as above here where everything's labeled. So so again, the water comes close and hovers, and then if there's enough of some interference, in quotation marks, then the sodium will break off, the chlorine will break off. Okay, so again, there has to be enough forces here to overcome the ionic bond and weaken it. Okay, so you'll get a few of these ions coming off, but if you got tons of water, yes, you could completely dissolve this crystal. Okay, but we're going to look at situations next day where there's always a threshold. Okay, so if you don't have enough waters or coming close to the crystals, or you have too many crystals, then the crystal will stay intact. But again, we just threw in one little tiny crystal into a big container of water, and so water's coming in and completely going to dissolve this structure here. So they call this process here where it surrounds it hydration. Okay, so the ions are being hydrated. So basically they're being surrounded by water, so that now the sodium and the chlorine can't come back together and make the ionic bond. Okay. So then when you get this hydration happening here, then you're going to completely dissolve the sodium chloride in the water, and then it'll stay in solution. All that stuff I just said, I have it kind of in little point form here, so you can go back and read it over if you need to. But I just tried to put a lot of visual things in here so that you can kind of see what's happening and so forth. Okay, all right. So basically they call this process dissociation. The sodium and chlorine ions are coming apart and being dissolved into water. So sodium chloride has been dissociated. So there is a dissociation chemical equation, and you've actually done this already with the ionic and anionic. So again, like you have those balanced chemical equations, but what's actually happening when you're in a solution with water as a solvent and so forth, that the compounds in the balanced chemical equation are actually floating around as ions. So this is what we did here. We broke it into ions. We wrote the state symbol as aqueous, right, because it's floating in water. So again, if you want to look at it from a different perspective, you are going to write aqueous because these ions are hydrated, right? So now you can actually visualize what was happening with the net ionic when you were writing this stuff. Though those ions were being hydrated with water. Okay, they're being surrounded with water so that they, when you dump a solid like this into water, this is what it looks like. It's not just NaCl like that. Okay. All right. And again, water isn't written in this, chemical equation, but it is an important part of the reaction. It doesn't actually break apart and change, but it's necessary for the reaction of sodium chloride breaking apart for that to happen. Okay. We've looked at ionic compounds like sodium chloride dissolving in water. So this applies to any ionic compound being dumped into water. Okay. All right. So now what we'll do is we'll look at the counterpart, the covalent compounds. Okay. So the ionic compounds were metal and nonmetal. So the covalent or molecular compounds are the ones where they were nonmetal. Okay. So what's happening with them when it comes to mixing into a solvent and so forth. Okay. All right. So we've touched on this in the past, where we know that covalent compounds they'll dissolve sometimes and sometimes they don't. So there's where ionic was always they dissolve. Okay, it was a property of ionic compounds, they would dissolve nicely. So molecular compounds, so some of them will dissolve, some of them just won't. Okay, so we're going to look at some examples today. So as you're going through, you're like, this is a lot of notes today. I just want you to kind of get the general idea. I'll kind of do a summary at the end of what you should pick up. I just want to give you lots of examples today, so you can kind of get a good, comfortable understanding of just the whole idea of mixing things and when things don't mix, what's happening, and make connections with intermolecular forces and so forth. Okay, so there's a couple, like here I have a couple things listed, like sugars. The sugars like glucose will dissolve in water. Okay, um, liquid ethanol here will dissolve in water, and it'll mix and it'll be fine. Okay, but there are things like oil. Oil doesn't dissolve in water. So, but these are all like, ethanol, glucose, oil. These are all covalent compounds. Okay, so they're made up of, see, like carbon, hydrogen, and then sometimes you have the oxygen and so forth. But you don't. Sometimes it'll just be carbon and hydrogen. But the main thing is you don't have a metal, non-metal. You have non-metal and non-metals all being combined here to make these compounds. Okay. All right. So there's some terms that I just want you to pick up right now. So when you see them in this note today, you understand what's going on. So miscible. Um, so basically, like soluble, like we're going to be using soluble a lot as well. Like I think I went over some of this terminology earlier. So we're looking at, the ability of things to mix together. Okay. So miscible, immiscible, right? Miscibility. These are just like kind of within this umbrella term of solubility. This is when we're just studying liquids mixing with liquids. Okay. So we'll use the word miscible. Where soluble is more of a general term. So if you use soluble here too, it'll be fine. Okay. So miscible, if you are miscible, so if you have a couple substances that are miscible, that means they can mix together and make a solution. So that way you don't see the separate parts and so forth. Okay. So yeah, ethanol and water. So ethanol is liquid, water is liquid. Those are both, they can mix together. There are some substances that are immiscible. Okay, so like water and oil are both liquids. Those don't mix together. Okay, so miscible, immiscible. Okay, and miscibility. Okay, so again, just the umbrella term to describe liquids mixing with other liquids and so forth. Okay. All right, so let's look at the first couple here. So again, I don't expect you to have to memorize glucose or the ethanol formulas and so forth. I just want you to kind of just see the general structure and then see how the intermolecular forces come into play here. Okay, so here's ethanol and water. So we already talked about how they do mix together. So this picture here is oil and water. Okay, so if you're just wondering, this one's oil and water. Okay, if you're referencing this note later. So yeah, we're looking at ethanol and water. So that's the stuff down here. So if you look at both of the molecules here, you hopefully are very comfortable with the water structure now. Here is the structure for ethanol. So you have, CH, right? A bunch of CHs, and then you have this OH at the end, just like water has an OH, okay? So water has the two OH bonds, one here, and then ethanol has one here. So like we looked at this already, whenever you have an oxygen, right, um, hydrogen bonding to a hydrogen on another compound, that's a really strong intermolecular force, right? So because, both of these have that OH, so even if it's like, kind of like that, and then this one has an O this way, the O and the H on the opposite elements here are hydrogen bonding together. Okay, and so when you can bond together like that, then you can mix together. Okay, so that's how this is working here. So if these are the compounds separately, but here they are where they're actually being hydrogen bonded together. Okay, so if you're looking here and so forth. Okay, so here, this is kind of more. This isn't really labeled. It looks a little off here. So the white goes to the red. That's good. But then here the white and the white are going together. So that means hydrogen, hydrogen. So this is a little bit incorrect. But if you look here, the hydrogen and oxygen are hydrogen bonding. Hydrogen, oxygen. Okay, so you want to see that. Okay, so I think they just made a little mistake with this one, and it should have gone to like the red here. Okay, instead. All right. Yeah, and see this one's going to the black one and so forth. Yeah. Okay. It's probably just like the angle of this picture. So So anyway, these two are miscible because they can hydrogen bond together because they have those, the OH bond, okay? All right, glucose. Here's glucose. So again, if you're looking at the general structure, some of you are taking biology, I think, had to memorize this. So again, if you can see, there's a bunch of OH branches on here, okay? So because you have that OH bond again, you can create a hydrogen bond. So again, if we just exaggerate this, you can create a hydrogen bond with the oxygen here, okay? With the hydrogen on the water here. So again, if you can give rise to these intermolecular forces, then that means you can stick together and you can, mix together and so forth. Okay, so that's why if you have, these if you have a polar molecule, okay, so you have these polar ends to it, even though this end here is not polar, but this end is polar, you have the ability to H bond. So that means then you'll be miscible. You can mix together. So we've looked at a couple substances that do mix together with water, okay? All right, so now we're going to look at a substance that doesn't mix with water. So here we're going to look at oil and water, okay? So here, our picture here that we looked at already, see they separate and they form different layers. And as soon as you form different layers, you don't have a solution anymore. You can see those different layers, okay? So we're going to look at and analyze what's going on here with oil and water. Okay, so yeah, water is they call it a universal solvent a lot of the times because yes, you can mix tons of stuff into it and it's fine, but yeah, there are a lot of things that don't mix with it, okay? And so here we'll look at some examples. So hydrocarbons, what are they? Hydrogen and carbon, that's what that is, okay? H's and C's. So here is hexane. So you're going to learn to name these so with your, more nomenclature next year. So kind of just a general here. There's 6 C's, and that's how you say hexagon, 6 of them. So hexane, okay? So anyway, so these hydrocarbons are not miscible with water, so they're immiscible, okay? And the reason why is that these are nonpolar. So if you go through and, actually find the electronegativity of carbon to hydrogen, this bond here is polar, but overall, because hydrogen's all on the outside, it's all partially positive, all on the outside, and then the carbon's all partially negative. But because you don't actually have a positive and negative end, you don't have poles, you are nonpolar. Okay, so yeah, hexane, it's found in oils, and because it's symmetrically shaped, right? We looked at kind of the shape of compounds, right? And so when they're symmetrical like that, and even if they have polar bonds, overall, they aren't. They don't have They don't have poles. So so you have a nonpolar substance here, and so that means, remember, when it comes to intermolecular forces, nonpolar and nonpolar compounds will bond together using London dispersion force, LDF, right? So remember, and that's the weakest of all the forces and so forth. So okay, so the main thing to take here is that because this is a non-polar compound, and water is a polar compound, there will be no H bonding, right? So to attract them to each other, and so basically, yeah, so they just won't mix together. I'm going to show you more of a visual here to explain what I just talked about here. So I want you to think of, like, you take some oil, you dump it in to water, and then you shake it up or you stir it up, and then you kind of have, the oil doing this, right? It's all kind of mixed and everywhere. So it looks like, oh, maybe it's going to mix. But then once you wait and let it settle out, this is what happens. The oil ends up at the top, and then the water's at the bottom. Okay, so if you wanted to kind of look at, like, if we could see the particles inside, these ones here that have nothing on them, that are a little bit browny yellow, think of those as being the oil particles, okay? So basically right now they're all kind of mixed together here. And then these other ones here where there's, looks like, I don't know, Mickey Mouse, right? So you have, this is the oxygen and those are the hydrogens. Okay, so it's the oxygen and those are the hydrogens, like that. So these are the water molecules also mixed in here. So what's going to happen is, so again, these are nonpolar, right? The oil is nonpolar. And the water is polar. Okay, so the water is polar. So, so you mix them up, and what's going to happen is that the water likes to H bond with other water molecules, right? So see, this negative end is trying to attract the positive end, right? Or will get attracted to the positive end of this water molecule. This positive end of the water molecule will attract to this negative end of this water molecule. So they're seeking each other out using the H bonding. It's not going to bond with the oil because it's non-polar. There's no poles to it, right? So it's not going to attract to these. So instead, what happens is that you, the water will seek out the other waters. And then if you go to this next one here, it's like then the oil gets pushed out of the way, so like the water is getting closer, right, to each other. And then the oil is getting kind of pushed out of the way because it's not being attracted to the oil. Okay, and then so then as it starts to settle and so forth, then now all the water is all H bonded together. They're happy they're together, and then the oil's been pushed out and away, and and then because of density, the oil ends up on the top and so forth. Okay, and now the oil's together here, and the water's together. So that's what's happening here when they're not mixing, and then they end up separating. So here again, and here's another diagram as well. Okay, so you're going to still get some, LDF, London dispersion forces happening here, but the hydrogen bonding is so much stronger that the water molecules end up just seeking each other out and then attaching together and then pushing the oil out of the way. So what we looked at here is polar molecules will mix together, polar and nonpolar molecules will not mix together. So therefore, nonpolar and nonpolar will mix together, right? So, if you have we're looking at like iodine here, right? It looks like this, right? It's a linear compound. So again, it's nonpolar. It will happily mix with the hexane or, the substance that we had above there, the oil, okay? Because they are both nonpolar. And, using London dispersion force, they will, attract to the hydrocarbons and so forth, okay? So that it'll dissolve. So it is a bit of an issue, I guess, out in the environment and so forth. Like there are some pollutants that are nonpolar, and all animals and humans and so forth, right? They have fats in their bodies. So basically, if they can get the pollutants in their body, the pollutant will actually dissolve into the fat. Where, normally, if you take some water and drink it, you can wash some stuff out of your body, right? But if it's something that is nonpolar, the water isn't effective at getting rid of some stuff here. So, so it's a big problem right now because if you get a pollutant into the water and then, I don't know, it gets into the fish and then something else eats the fish and then, so it keeps getting stored in the fat of whatever predator keeps coming along, and it accumulates. It doesn't get washed out or cleaned out of the body. It just stays in there, okay? So it's a big issue here with just when they decide to use some sort of insecticide and so forth, they have to be really careful about the consequences of it. So what you're supposed to just take from, me showing you all those examples with oil and water and glucose, like sugar and water and alcohol, ethanol and water, and just iodine and hexane and so forth. Okay, so the main thing here is that if you are polar, you will mix with something else that's polar. If you're ionic, you'll mix with polar substances, okay? But if you are nonpolar, you will mix with nonpolar solvents and so forth, okay? So they like to use this term or this little phrase, like dissolves like, okay? So like things will mix with other like things, okay? All right, here I just wanted to give you another example here. Capsaicin, it's a substance found in chili pepper. So basically, if you eat something that has chili in it, you'll find that your tongue's burning and it's hot and so forth. So it sends signals to your brain that, oh, you just ate something really hot and your tongue's on fire. Okay, so I, so if that ever happens, like people try to drink water and it doesn't do anything. It's just like your tongue still feels like it's burning and so forth. So what they recommend is that you drink milk, right? Because milk has fat in it, and the fat, right, is nonpolar. And the capsaicin is actually a nonpolar substance as well. So if you take those two, mix them together, you will get, the milk can dissolve the capsaicin off your tongue, and then yeah, kind of alleviate that pain that you're having on your tongue. Okay, so just a neat example there. Okay, I just wanted to just talk quickly about surfactants. It's soap. Okay, um, these so soap, like the particles, they actually have both properties of being polar and nonpolar. So it's kind of an interesting compound. If you're taking a look here, so again, this looks kind of like the hexane, right? So you're just seeing a symmetrical part here where this is going to be the nonpolar part. But then you see that oxygen, right? The O, like whenever you see the oxygen coming off, right? So this end will be polar. Okay, so an interesting substance here called or surfactants. They so it's just they're soap. It's soap. It's like detergents and so forth. Okay, so if you the neat thing about these is that they exhibit both polar and nonpolar properties. Okay, so here, if you take a look here, it's just sodium stearate and sodium lauryl. Okay, so if we, yeah, like we have our cation here, sodium. So there's our cation, and then the rest of it here. So the negative here, this is the anion. Okay. All right, so we're just going to be looking at the anion here now. So here, let's put anion on this end here. This is the anion. Okay, so so that's the negative part. So like even if I wanted to just cross off the sodium and put sodium right here. Okay, so that's the cation here. Okay, so the anion part is interesting because it has both polar and nonpolar properties. So if you take a look here, so they considered this part to be the head of the anion. Okay, so kind of where the oxygen and the carbon oxygen is, and the rest of it kind of looks like, like the hexane that we just saw, the oil, where it's just symmetric and it's all surrounded by hydrogen like that. The carbon's in the middle. So this is the tail end. Okay, so they say that, okay, so the head end here is polar because you have that oxygen, right, that can hydrogen bond to things, and then the tail end is non-polar because it's pretty much symmetric. It's this carbon surrounded by hydrogens here. Okay, so when they draw these out just quickly on diagrams, they'll just make the head and then they'll make the tail here like that. Okay, so so they, because you have the nonpolar end, they call these ends, like this is the hydrophobic and hydrophilic ends. Okay, so that just the fancy way to say, so philic means to like. Okay, so the yeah, means to like, so you love water. And then hydrophobic, you hate the water. Okay, so kind of a good way to remember it. All right, so and then, like, I don't know if you want to, you can call it amphiphilic. So they exhibit both properties of this ion. Okay, all right, so again, if you're getting a little bit over on it, the main thing I wanted to show you here is that it has both. It has both a non-polar end and a polar end to it, and so it's a neat little structure. So because of that, soap is really effective at getting rid of dirt. So we'll show you how that works here. Okay, so basically, you're going to take your soap, and then you're going to take your water and start lathering it up. Okay. And then, so when you do that, then the sodium dissociates, right? And then you have this, you have it in ion form. So you have this anion now. So what's going to happen is that, again, so you have water, right? So we're going to have water in here as well. So with our anion here, so the head end here is going to hover towards the water, right? So maybe I'll put the water closer to here, this end here. All right, and then the tail end will not won't go near the water. It won't be attracted to the water. Okay, so and so if you have a dirty shirt, say, okay, so here's it says skin here, but we'll pretend that it's a shirt here. Okay, so we have a shirt here. It's got mud or oil, let's say it's oil. Okay, but we can say that it's dirt too, because dirt is nonpolar. So we got some oil on our shirt here, and so basically now we throw it into the washing machine. We have detergent in the washing machine. It's all mixing up in here with water, and so what's going to happen is, so since the soap detergent is in water, it'll dissociate. So that anion here will now be on the loose. Okay, so this anion piece here, and what will happen is that it'll kind of float around, and then when it gets close to the dirt here, okay, remember the tail end is the nonpolar end, right? So it will attract to the nonpolar oil. Okay, so say this is dirt or oil here, right? And so it will get attracted, so that the tail will get attracted. So see how the tail is sticking onto the dirt here? So so what will happen here is, so yeah, it'll attach, but then remember it's a washing machine, so the water is swirling around and so forth. So remember this end here is polar, right? And it's going to be attracted to the water. Okay, so then the water, make water here. Okay, so this is all in water. So then the head end here is going to be attracted to the water, and the water is being swished around here, right? So, and then remember the water is all hydrogen bonded to each other and so forth. So it's being mixed around here. So basically, what happens here is that when the water is being moved around like this, it'll end up pulling this dirt up, like pulling up on the head of the soap here, right? And then the soap is the tail part is holding onto the dirt, so then the dirt will get pulled off the shirt. Okay, and so then when that happens, and now the dirt's floating in the water, the other tails, the other anions will come along and just surround it like this, and they call this a micelle that it creates. Okay. So, and then basically once it's surrounded like this, the water will be around it like this, right? So now this piece of dirt can't go back and, go back into the shirt. Okay, so it gets cleaned, and then eventually the cycle will drain, and then this will get drained, just sent down the drain and so forth. So so I wanted to introduce you to surfactants and soap, and how soaps work, and how soap uses intermolecular forces with water in order to clean things and so forth. Okay, so that leads us into a topic that that's in the news a lot right now. So I just wanted to explain to you, when they're telling you all the time that you should be washing your hands, so that you can keep yourself safe and so forth. So I'm just going to finish off this lesson by applying kind of what you've been studying to the COVID-19 virus. Okay, so why are they telling you should wash your hands? So you've seen the coronavirus pictures everywhere. So it kind of has this shape here, and it looks like the sun. So that's why they called it the coronavirus or COVID-19. Okay, so the structure of it, I'm just going to go over the general structure. Like these spikes here are the protein structures, but where the sphere part is, that's actually made up of lipids, which is made of something similar to fat. So it's like you have a fat envelope or blanket here. Okay, so the coronavirus has this fat blanket here, and then remember, fat is nonpolar. Okay, so this is nonpolar here. So what happens when you actually go, like if you have coronavirus on your hands, what happens when you go and wash your hands with soap? So you take water lather up the soap. So what's going to happen is that, again, the soap is going to dissolve, right? And you're going to get this anion floating around now. And the anion, remember, has a polar head and a nonpolar tail. Okay, so it can attack it just like that dirt on your shirt here. So what's going to happen here is these anions here, they're going to attach, right? Just like they did with the dirt. The nonpolar end is going to attach to the fat part of the virus here, and then it'll attach here. And then again, you're washing your hands with soap. So then when you do that, the water will pull off the soap, right? And in that process, you're getting your hands clean, but and then they say for 20 seconds you're getting your hands clean, but on top of it, that whole process will actually destroy the virus too. So it's not like it can come back and infect someone else and so forth. So the soap will actually break apart the virus here. So it'll rip it apart, and then just like with the dirt here above, it'll, like, once it's broken apart, the other soap particles, the anions, will come around and surround it like this. And then you're washing your hands. It'll make a micelle. And then you're washing your hands, and then you're washing it away down the drain. Okay, so I know there were a lot of notes today. Seemed like a lot of stuff, but like in the end, these are the two things that I want you to take from today. Can you explain to me now how you would take an ionic compound like salt, sodium chloride, and dissolve it in water? Okay, so if you're taking a look here up at the top here. So again, we put in our crystal of water because of the polarity of the water molecule. It came and it disrupted the ionic bond and broke it apart, right? And once the ions start flowing around, the waters will hydrate that ion so that they can't go back together, okay? So you should be able to explain the whole idea of dissolving and why water is such a great solvent, because it's polar, and then it could break apart ionic substances like that, and it mixes with other polar substances, okay? And and then the other part that I want you to take from today is like dissolves like. That's the main thing, okay? So you should know if something is polar, it will mix with something that's polar. If something is nonpolar, it will mix with something that's nonpolar, okay? But then if you have a polar and a nonpolar trying to mix together, it's not going to work, okay? And then I just tried to show you lots of neat little examples, like with like the soap and so forth. Like, you don't have to know all of this stuff, but I just thought it'd be neat to see like how intermolecular forces and hydrogen bonds and how they lead to a lot of interesting things, like how, like soap, right? You can clean off the dirt on your shirt, or you can destroy, the coronavirus and so forth using water and soap. Okay, so so just the main things: be able to be comfortable with just understanding how water is a great solvent and what it does when it breaks apart an ionic compound, and then just know that polar and polar go together, and nonpolar and nonpolar go together. Okay, so just try some practice questions and then the checkpoint.